Adding whole numbers has a very natural interpretation. If I have this many over here and that many over there, how many altogether? Well, just join the groups and count them up. We use words like add, plus, more, join, together, increase. The simplest strategy for adding is just to count on your fingers. Of course, more than 10 and you need toes as well, and then you'll run out of those too, so you might need some counters or other physical objects. Working in base 10, we can also use some special kinds of objects and shapes to help us to subitize, which is a fancy word for counting quickly by grouping in easily recognizable ways. Often we'll use a row of 10, a square of 100, a 3D box for 1,000. For simple questions and small numbers, use mental strategies. Basically, learn by rote some basic addition facts. Does this sound a bit old-fashioned? Actually, learning the basic facts by rote means you have more brain space available later on for the hard stuff. I'm a big advocate of learning and memorizing basic number facts. Of course, you can also use other strategies mentally if you need to. Imagine a number line, or visualize yourself writing the numbers and doing the sum on an imaginary piece of paper. The number line is a very useful tool for addition. You can just count along it, or you can move in jumps for tens and then units, teaching grouping and make-up strategies as students' skills improve. There are many standard written algorithms for addition that work for adding 2 or more whole numbers, and they can be easily extended to decimal numbers later on. The Australian curriculum doesn't specify any particular algorithm, because the emphasis is on teaching students a range of computation methods and strategies. Students are to learn to be able to calculate answers efficiently and choose appropriate methods. In fact, the Australian curriculum doesn't say that students need to be taught a standard algorithm at all. What we really need to do as maths teachers is guide our students towards more efficient strategies, which may include the standard algorithms, and help them learn how to choose which methods to use when. And of course, there are calculators and computers for when the numbers get larger and the situations more complex. It is important that students learn what addition is and means first. We don't want them just treating their calculator as a magic black box. That won't help them at all later on to know when and why to add, or subtract, or multiply, or divide. Subtraction is the opposite of addition. If I have this many, then I take some away, how many have I got left? Subtraction is also the underlying operation for comparing two numbers, or for equalizing two groups. How many would I have to add to this group to make it have the same number as that one? Words indicating subtraction include take away, reduce, minus, subtract, decrease, without, difference. Also questions like how many more or less, how much bigger or smaller. The strategies for subtraction are the same as for addition. Use fingers or counters or other objects. Move backwards along a number line instead of forwards. Notice the natural way that walking forwards and backwards for addition and subtraction can correspond nicely with a well-established convention that a number line increases from left to right. This is why it is so important to set and to reinforce simple conventions like this. Later on, when we start adding and subtracting negative numbers, we can build on this same strategy and convention to help students to understand and work with more difficult concepts. Multiplication is just repeated addition. It's indicated by words like times, product, of, by. Be careful though, many of these same words are used for division as well. The standard symbol for multiplication is the cross. When we get to algebra, though, we often use just a single central dot, or even omit it entirely. Please be careful when typing mathematics, including on PowerPoint presentations, that your times sign does not look like a letter X. Make sure it doesn't have serifs. And in the same way, when doing algebra, we need to make sure that our X's don't look like times signs. We represent multiplication by going back to its meaning of repeated addition. For example, to multiply 3 by 4, you could make 3 groups of 4 objects each, or put down 3 sticks, each of length 4, or make an array with 3 rows of 4, or equally 4 columns of 3. See how the meaning of repeated addition helps us to arrive at the correct answer. Reinforce that meaning all the time. Again, when the problems become harder, like with fractions or algebra, the meaning of multiplication being repeated addition will help our students to understand what's going on, even when they can no longer physically manipulate the objects they're multiplying. Indeed, the idea of multiplying with arrays is fundamental to the explanation of the distributive law later on in algebra. But that's a story for another day. Personally, I feel it is vital, for our students to know their times tables off by heart. Why? Well, it's about the way our brains work. Your short-term memory can only hold about 5 to 7 things at a time. That's a hard physical limit. It's just the way God made us. The thing is, later on, the maths problems get more complex, and it's hard to keep everything in your head. If you don't know your times tables, then every time you have to do an operation as part of solving a complex problem, you have to think carefully through the multiplication or whatever, and then you've forgotten where you were up to in the problem. It really does make it very difficult to solve anything hard. Having a calculator doesn't help you with this either. By the time you find it, turn it on, type in the numbers, oops, made a mistake, try again, and then you've forgotten where you were up to again. You really must know your times tables. And of course, as a teacher, it's even more important for you to know them. You need to have a good number sense, so you can have a good idea right away whether a student's answer to a question is about right. This goes along with the skill of estimation. It helps you to know what kind of answer to expect and whether the answer you've got makes sense. Finally, division is the opposite of multiplication. How many times does this go into that? How many groups can I split this up into? Division is indicated by words like times, groups, share, into, between, of, and also by more specific words like quotient, factor, remainder. Notice how many of these words can also mean multiply. There are 3 standard symbols for division. The first, that short horizontal line with 2 dots, is actually really just a small fraction sign. Can you see the dots for the top and bottom of the fraction? In fact, the line in the middle of a fraction just means to divide. The slash is becoming more common nowadays as people use computers to type their maths. Personally, I prefer the real division symbol, but most keyboards don't have a key for it, unfortunately. And then, when we write out the division algorithm by hand, there's the square corner symbol that gets used to separate the numbers. Now, dividing really is just the opposite of multiplying. If you know your times tables, that's pretty easy. If you want to represent it physically, try the same ideas. Can I break this set of 12 things into 3 equal groups? How many will be in each group? Or, can I put these 12 things into a grid with 3 objects in each row? How many rows will I get? But the really interesting questions come along when it doesn't split equally into groups. If I have 13 coins and I want to divide them up equally among 3 people, what do I do with the one left over? What do I do with the remainder? Do I keep it myself? Does one person get more than the others? In the old money system, I could split a shilling 3 ways by giving each person 4 pence. But in our metric system, it just can't be done. What do you think? What do I do with that last coin? Would your answer be different if they were lollies or pizza or something else you can break up into smaller pieces? Or dare I say, fractions? You see, it really depends on the context, and it can be quite tricky if you can only use whole numbers to give the answer.